Okay, let me start. Is this good? Test? Yeah, okay, good. Okay. I'm Subha, so you can interrupt me anytime if you have a question. And in an hour or so, we will have a break for like serious questions. So, yeah. And then we will have coffee break and then again the next part. So, let me tell you the plan for today. So, I'm going to discuss something called quantum walk algorithms today. Is this visible to everyone? Perfect. Okay. So the plan is going to be, I'll discuss something called an MNRS framework of quantum algorithms, which is walk-based. We're going to have the setup and what it looks like. All these analysis will be here. And this is going to be part 1 of our lecture. And in part 2, I'm going to discuss application of these walk-based algorithm for certain computational problems. I'll be discussing 2 computational problems. One is element distinctness. Don't worry, I will define everything. And the other one is something called three-sum problem. And we are going to discuss the time complexity and query complexity for both these problems by giving a walk algorithm to solve them, okay? And this is going to be part 2. And the third, last part is going to be a technique to give something called conditional time lower bound for three-sum using, again, quantum walks. And this is going to be part 3. And this was a result we obtained while I was doing my PhD. So it relates to quantum walks very naturally. And we'll see all these 3 elements today. Yeah? Okay? So let me begin. Okay. Now, everybody is familiar with bra and ket notation, so I don't have to go through that. And we are also familiar with unitary evolutions of quantum states, so I'm not going to discuss that. And also measurements. And I'm going to be sticking to computational basis measurements throughout the talk, okay? Now, what I'm going to discuss now is called something called query algorithm, okay? Now, let's first see how computational complexity people look at a certain challenge, okay? Now, imagine I have a Boolean function. For example, the OR function. How many of you know the OR function? Oh, wow, awesome. Very nice. Okay. I took the perfect function to start with. So this function is defined on n input variables, and the output is a Boolean outcome. And the function is defined this way. So OR of x is equal to 1 if there exists some index in 1 to n, or this is the Hamming weight, greater than or equal to 1, and is 0 otherwise, right? Yeah. Now, if I ask you, what is the amount of resource required for me to compute OR? And what do you mean by computing OR? I will give you an unknown input, like input, unknown. Unknown, we will come to this part as to why this is unknown. And now, this input is like a capital N bits long string, right? So we have x2, because I said the input, like the OR function is kind of defined on this domain. So these are all capital N bit strings. So I'm giving you an input x, which has n bits. And now I want to compute OR of x. That's the task, okay? And when I say I want to compute, I want my computer to compute that value, okay? Now the task is, my computer can ask me a question, oh, what is the value of, say, x1, okay? If it says it is 0, I know that I cannot conclude the value of OR yet, right? I'll have to ask another index. Say it tells me, and next, my algorithm says, oh, what is the value of x2? I say it is 1. Then I know that I don't need to compute anything, like I don't need to ask any more questions, and I can immediately output OR of this x equals to 1, right? So this is kind of clear. Now this asking, when I give an index I and I ask, oh, what is the value of xi? That is a query to my input. And in this world, we are going to talk about query algorithms where you have an input x, it is like an oracle. Now my algorithm can access this oracle OX, and it will give me the output of xi. And I can, by like constantly asking these queries, I have to evaluate OR, okay? Now, classically, the number of queries required to compute OR turns out to be order omega n. Yeah. You have a question? No. Oh, no. Okay. No. Yeah. And quantumly, any idea? Yes. And because of? Yes. Now, quantumly, what we have is you can come up with a query algorithm that solves OR, and the cost is only square root of n, as opposed to, this is quantum, as opposed to classical, where the number of queries required is n. Yeah? And people are familiar with big O and omega notation? Not really? Okay. You can imagine big O notation as something like there's some constant hidden in there, okay? And it is less than some constant times root n for very big n's, okay? And the omega notation is kind of, again, there's a constant hidden, and you can imagine this to be greater than some constant times n for very big n's, okay? Yeah? So is the setup kind of a bit clear, like what the challenge is? The challenge is we have to compute a function, and we are given these input in this way. We can ask questions to the input, and you can find the output. Yeah?
And so you said it's greater, but maximally also n, so it's like exactly around n?
Sometimes with randomized algorithm, you can save some constant factor, like maybe it will be n by 3 or n by 4. So to be on the safe side, I just put big O, big omega notation. Yeah. In the deterministic setting, like if you don't allow your algorithm to make any random choices, then it is indeed capital N. Yeah. Okay. Now let me just tell you how the quantum query algorithm looks like. So you have some m qubits to begin with, okay? You're allowed to apply unitary operations on it, okay? You're allowed to apply this query oracle on it, and the query oracle is like you give an index I give you xi, but now because I'm in quantum world, I'm allowed to ask this query in superposition. I will define how OX looks like, the action of OX. Yeah. So I say a query algorithm A computes a function f. It doesn't have to be OR. We can come up with query algorithms for any function, any Boolean function. It need not be OR. We say a query algorithm A computes f if by the end of it, when you measure this first qubit or something, you kind of get your answer f of x with probability. So you have, suppose this measurement outcome is b, you get your probability that b is equal to f of x is greater than equal to 2/3. Okay? This is a bounded, one-third bounded error quantum query algorithm for computing f. Okay? And this Grover's algorithm, there is a famous algorithm by Grover's, which uses this kind of a model to compute OR, and gives for OR, you have OR on n bits. Okay? I'm not going to discuss the Grover's algorithm today. because that's little out of the scope. But we will discuss similar query algorithms for the walk model, okay? Yeah. Cool. So any questions on what the OX oracle in some sense does this. You give an index I, you give some register B, okay? This gives me the value of I again, and it gives me B plus xi. Yeah? So what it does, if your B was initially 0 and your xi was 0, then it will just return 0. But if your B was initially 0 and your xi was 1, it just flips. It flips the value of B, okay? And this is a reversible process, and this is a unitary operation. So you can even act this on superposition of different indices. Yeah? All this setup is clear? Yeah.
Maybe the two-thirds, is it like just something bigger than one half, or?
No, not just something, a constant bigger than half. Because if you want to have the probability like very close to, say, half plus 1 by 2 power n or something like that, then it's a different class itself of problem. So this has to be some constant bigger than half. Yeah? Any other questions till now about the model? Because till now we haven't even looked at what walk looks like. Yeah? Okay. Now one thing to notice here is we people in complexity theory, what we care about is how the resources compare to the length of the input. Okay? So if my input is n and my resource, the amount of resource I use is root n, then I'm very happy. But if the input is n and say the amount of resource I end up using n cube or something, then I'm not that happy. So the resource kind of is measured by the length of the input. Yeah? Okay. Okay, now let's start with the walk thing. Okay. So, yeah. No, this doesn't look as if it'll work. Is this visible? Okay. Now we are going to move to a different setup. What we have, say a graph, G. It has some number of vertices and it has some edges, okay? Now I'm going to give you some properties of this graph. It's undirected. It is, the number of vertices is say n. And I have like a set of vertices, which is a subset of this V. And I will call this as marked vertices. And the number of marked vertices is some epsilon fraction of n, okay? So I'm just drawing a random graph. Suppose this is all this graph. I have V1, V2, V3, V4, V5, V6. Now I'm drawing a undirected graph. The undirected graph says that there is no direction for the edges, okay? So now the vertex set for me will be V1 up to V6, right? And the edge sets will be like V1, V2 or V1, V3, so on, yeah? This is a simple graph. Now imagine I have some marked vertices. Say these are my marked vertices, okay? Now the task, I'm given a graph, some graph, and the task is to output a marked vertex. Okay, that's the task. And you're given the promise that there will be epsilon fraction of these vertices that are marked. Now, how would you do it? So, and imagine I can tell you, oh, by looking at a vertex, I can give a check procedure which says, oh, is this vertex marked or is this vertex not marked? Yeah, that is possible. So what would you do in such a situation? Yeah?
Pick one vertex at random, look at its mark, go to neighbor.
Yeah, okay. So the algorithm suggested is like you pick a vertex at random, pick a vertex V in this capital V at random, check if it is marked. output yes, if it is. Else, what do you do?
Go to some neighboring vertex.
Something simpler, where we don't want to go to neighboring vertex?
To some other random.
Exactly. So you again pick. So this is a valid procedure, right? So what I'm doing here is I'm picking a vertex at random. I'm checking if it is marked. If it is marked, I output yes, or V is marked. Otherwise, I go back to step 1 and I pick it up again. Now, what is the probability of success for me? Half? Someone said half? No, it's epsilon. Because you have epsilon number of like fraction of vertices marked, right? Yeah.
In the example, it's half.
Ah, yeah. Oh, okay. I see. I see. Yes, yes. In the example, it's half. Yes. But in a general case, it will be epsilon, right? Now, how many number of times would you want to repeat this step to kind of be sure that, not sure, but almost sure? 1 over epsilon, yes. Because that will be the expected number of times you will run the procedure, and then you will hit a marked vertex, okay? Now, if you can use Markov's inequality here, and then you can even bound that with high probability, you will never have to cross more than, like, too much more than the expected value of steps. So I can say, in about, okay, I'm going to use now sloppy notations, meaning I'm not going to count exactly, but in about this many steps, I can find a marked vertex, right? So, and this is kind of clear because if epsilon is really small, then I need a lot of steps to find a marked vertex, okay? Now, what if I don't have this sampling procedure? What if this procedure for me is not possible? Because for some reason, the graph is not given to me implicitly. It's given implicitly. I only know if I am at a vertex, I can explore its neighbors, but I can't really sample. Then what can we do? Any idea? Yes. As the title suggests, we are going to walk on the graph. And how are we going to walk on the graph? We will start at a vertex. Let's say the starting vertex is given to us. We'll start at a vertex. We are going to uniformly at random pick one of its neighbor. And once we pick, we can either check, okay, is it marked or not? Or you can just take some case steps first. Like you pick a neighbor at random, then pick another neighbor of this V2 at random, and you go on, and then you check if it is marked or not. Both these procedures will work, and you can find a vertex by that. But what is the time complexity? Like how we calculated resources in the first case, can I bound now the number of steps I have to take before I find a marked vertex? Now that is going to be a walk-based algorithm to find a marked vertex. And before we deal in quantum, we are going to first look at a classical walk algorithm to find a marked vertex in a graph. Yeah? The setup is clear? Okay. And am I going too slow, too fast, or the pace is fine? Okay, good. Okay. Now let's discuss this walk-based algorithm. Okay. And I'm going to give you an algorithm, but I'm going to assume certain structure on the graph. And for that, it will be very clear soon why we are going to assume some structure of the graph, okay? Now, I'm going to assume that my graph G has the following property. It is undirected. It is connected. And by connected, I mean, you give me any two vertices, and I will be able to find a path between them. They are not disconnected components. They are all connected. We have undirected, we have connected, and we have non-bipartiteness. Yeah? Okay, these are, there was one more property. Yeah, and deregular, yes. And by deregular, I mean every vertex for all V, we have exactly D neighbors. Okay? Is the setup clear? Yeah. Oh, non-bipartite means you cannot kind of have the graph split into like two sets of vertices, V1 and V2, and have no edges between them, but have edges only across the sets. This is a bipartite graph. We don't want a bipartite graph. We want a non-bipartite graph. Yeah? No, I can have like a bipartite set like this, see? I will have like 3 vertices here, say 4 vertices here, okay? Now I have no edges between them, but I can do this. Now everything is connected because even to reach from here to here, I can still take a path, but it's not, it's bipartite. Yeah?
A question about the algorithmic complexity of the Grover search overfunction. So that is the time complexity, not the operating complexity.
It's actually both. So in Grover's, what happens is you can use, okay, so when you have a query algorithm, the query complexity is number of times this Oracle OX has been accessed, and the time complexity is also the number of gates in total, and you count the number of gates every unitary needs to be implemented, and you count OX as 1 gate, and this big O is going to hide all the extra constant factors.
But then how can you have fewer gates than you have qubits and still have the result be related to all the input qubits?
Oh, that's because like when you have Grovers, so in Grovers actually you can do it in log n qubits. So what happens with Grovers is you kind of construct a superposition of all possible indices, right? Do you, is your question like how can I compute something, like say for OR, which is on n qubits or n bits of information, but how can I do it in like log n bit qubits? Is that your question?
In gates. How can I do it in square root n gates on n qubits?
But this is not n qubit. This was some other n. Like this is.
But those are still representing our binary inputs, right? So like if I have n binary bits,
Yes.
I translate them into n binary qubits.
No, my input. I see what you mean. Okay, my input is not on these wires for me. My input is hidden in this oracle. Okay, we don't care about how the oracle is implementing it. We count this as one step. And this oracle gives me out the xi value when you give an index I.
Okay, now I understand.
Yeah, and the index I will only require log of the capital bits because that's the number of bits you will need to represent an index. Yeah? Okay, cool. Okay, coming back to this. Yes. So we have this clear with the bipartite question? Okay. So we have these conditions now for this graph. And we will see that how, if we walk enough, we'll always reach this place so that we can sample a procedure. Yeah.
Do we allow self loops?
No. Oh, good point. Yeah. No self loops. Okay. Now, we have these properties of the graph. And what I'm going to propose is, let's look at the adjacency matrix first. So the aim is, I am considering a situation where I'm not able to sample a vertex at random, and I want to implement this sampling procedure. So I want to reach to a point where, if I walk enough, the procedure makes me as if I'm sampling a random vertex from this set of n vertices. Once I implement this part, this first part, then I will just do the second part as it is. Yeah, this is what the aim is. And this is what the classical random walk is going to do. Yeah, now let's begin. Now, are you guys familiar with something called an adjacency matrix? Yeah, an adjacency matrix is kind of just remembering the structure of the graph. That's what the adjacency matrix does. Now, adjacency matrix is labeled by 2 things. It's labeled by a vertex x. Maybe I put vertex y here, and a vertex x. So this entry, which is a of xy, what it contains 1 if my edge xy is present in the graph. So this entry here for say v1 V2, it will be 1. Okay? Now, everywhere else, if the edge is not present, it will be 0. Yeah, that's clear with the adjacence matrix. Now, because it's an undirected graph, this matrix is going to be symmetric, yes? And I also mentioned that it is a D-regular matrix, which means every vertex has exactly D neighbors. So there'll be, so for every row, I will have exactly D ones in the row, and same thing for the column because it's also a symmetric matrix. That part is clear? Okay. Now I'm going to take another matrix called P matrix, and this is going to be just a normalized version of my matrix A. And what does this P matrix do? I just replace everything here, and instead of having 1, it'll have 1 by D. And the other condition is the same. If there is no edge, the value is going to be 0. Okay? Now what you can think of this P matrix is also, is this P matrix can be kind of seen a mathematical representation of making a walk. So if I start with a vertex V, suppose, let's see. Let me start with my vertex. I'm going to erase some parts here now. Yeah?
Is the D the same from the D regular? So it's the number of neighbors.
Yeah, yeah. This D is exactly the same D regular. Now I'm going to kind of tell you. Now we discussed what a walking is in literally walking steps. But now mathematically, what does this walk mean? If you have this matrix, this is a distribution matrix now. Walking is just multiplying with the vector which contains the distribution of your initial vertex. So if my initial vertex, suppose I said, oh, let's stick to the initial vertex as this. Let me call this as the start vertex, V1. And say my vertices are labeled as V1 up to Vn, like this. Now my initial distribution is going to be 1 at V1, and it is going to be 0 everywhere else, right? Yeah. Now if you just compute P times this V, these are just matrix multiplication, you will actually see that you will get a distribution which is uniform distribution over all neighbors of V1. You will get 0 at V1, V2 is a neighbor, so you're going to get half there. Or in this case, it is not a D-regular graph. Yeah, this graph is not D-regular, but imagine it was D-regular. So you're going to have 1 by D entries for all its D neighbors. And everywhere else, it is going to be 0. Now, if you take one more walk step on this distribution, the new distribution you would get is now the probability distribution of reaching like any of those vertices if you started with the vertex V1. You get what is happening mathematically? So this is what the walk operation does. And the reason why I kind of limited myself to these properties of graph is because if we have such kind of structured graph, we can analyze the spectrum of this matrix very easily, and we can use this analysis towards our algorithm. That's what we're going to do. Yeah.
Intuitively, why do we need non-bipartite for this?
Because what we actually want in the end is to converge at a distribution which is uniform at random for every vertex, like the same uniform distribution over all vertices. But if I tell you my starting vertex is just V1, that is not uniform at random, right? My distribution is concentrated here. But I want to reach a distribution which is uniform for all. Like, I want to reach a distribution where the probability of picking any vertex for me becomes 1 by n. That's my aim. Now, if I have a bipartite graph, I cannot converge to that distribution. Like, no matter how many steps I take, I will not be able to converge to a uniform distribution by just walking. That's the problem with bipartite graphs. That's why we restrict to non-bipartite case. Yeah? Okay.
Kind of following up on that question, how does this P matrix of a bipartite system look like?
Yeah, we are going to exactly talk about that now. So we are going to discuss now something called the spectrum of P. Spectrum is nothing but the different eigenvalues possible for P. And it is the eigenvalues that will kind of determine, like it kind of captures whether it's connected, whether it's bipartite, whether it is deregular, all these stuff. And we're going to use that, yeah. Tell me.
My question
Here? You mean here? With one walk step, because there are no self loops. That's what we also cancelled self loops. Yeah, yes, yes. By application of this P matrix, you're only going to make one walk step. I mean, of course, like if you take a couple of walks, we can come back. Yes. This is fine as of now? Okay. Now let's look at how the spectrum of this matrix looks like and how we are going to use it for our walk. Can someone tell me what the time is so that I have an estimate of how? Quarter to 9. Okay. Quarter past 9. Oh, shoot. Okay. Yes. Okay. Fine. Yeah. Okay. Now let's look at the P matrix. Okay. Now P matrix. My first claim. Let me just clean this up a little more. Okay. My first claim. Let U, the vector U, denote the uniform distribution over all my vertices. Okay, this is what I want to V1, V2, Vn. Yeah? This is a valid distribution, right? And it's a uniform distribution. Okay? Now, my claim is U is an eigenvector of P. That's my claim. And for a P that corresponds to graph with these properties, okay, not just any graph. Like my claim is if P is a stochastic matrix, which is the normalized adjacency matrix of a graph containing those properties, then U is an eigenvector of P. Can we quickly check? Yeah? Okay. Now what is the property that we need when something is an eigenvector of a matrix? What do we need?
The input vector is the output vector if we apply the matrix.
Sorry?
If we apply the matrix to this, it doesn't change.
Exactly. Yeah, yeah. So it doesn't change, but it could have a scalar multiplication, right? That's the eigenvalue. So what we want from an eigenvector is that if I have, like, the property of an eigenvector is something like this, right? I multiply the vector with P, I actually get some scalar quantity multiplied with the same vector. Now if you just replace U here, you will, it's just one step of calculation, it's easy to see that you will actually get Pu is equals to lambda being 1 times U. Yeah? And to immediately see, imagine you have this P matrix, it has some entries somewhere, right? And you multiply your vector 1, what do you get? You basically get D of these ones added, and you had 1 by D every entry in P, so that became 1. So every row just contributes to 1, so you end up getting the same vector. Yeah? Questions? No questions? Everybody's convinced? Okay. And we are also convinced that this eigenvalue is 1? Yeah? Okay. Now what I'm going to say is, for this matrix, we have some more interesting things. Now if I took all my eigenvalues and I kind of arranged them in descending order, okay? See, at max I can have n eigenvalues, right? It's an n by n dimension matrix. Now imagine I ordered them in descending order. It's possible that there are some eigenvalues of the same value, that's fine. But let me just put it in the order. Now what we have is, for these kind of matrices, we have your gamma 1 as 1, and it keeps decreasing, and your gamma n value is bounded, like it is greater than minus 1. So all your values you have from gamma 2 to gamma n between, lambda, yes, it's lambda. For these matrices, what you have is your lambda values are between 1 and minus 1, and not for lambda 1, okay? Yeah.
Does the left-hand bracket need to be a square one? Because it can be equal to 1?
No, that's why I wrote it from 2. Like, so.
Above it you had like less or equal.
Yeah, but I'm saying like for these matrices, for these P's, the lambda 2 is strictly less than lambda 1, and it follows this rule. Okay? Yeah. Oh, this is a stochastic matrix. It can even take like negative eigenvalues. It's just a eigen decomposition of your matrix. Yeah.
But why strictly greater than -1? Why can't it be equal?
Oh no, that is because of these properties. So, yeah. Yeah. I think I forgot which of the properties imply which kind of constraint, but all these properties combined give you this constraint.
It's because of the Kirschgården circle theorem, right? So the no self loops and the deregular.
Only that? I mean, I know that the fact that it is. Yeah, I have to think once, like why this is there. But for now, you can be sure that it is because of these conditions that your lambda for your P has these properties. Okay. Now, why this condition helps us is because now because of this, we can define some quantity called a spectral gap. Like we can define a quantity called spectral gap, which is 1 minus max of I greater than equal to 2 lambda I. Okay? And because this is in this, what is this? Range. Yeah, it is in this range. What we have is we have some promises also on your delta there. Okay? Now we're going to use this delta in a minute. Now what I'm going to say is, I'm going to claim something. Yeah. I'm going to make a claim. And the claim is, on these kind of matrices, no matter what vector, no matter what distribution you start on, there always exists some k that if you make k number of steps on this, walk on this graph, you will end up at this uniform distribution. That's the claim I want to make. Okay? And because of these properties and because of these properties of these lambda values, it ensures that you can reach. Now let's look at why we can make such a claim. Now, if I take one, say, what I want to say, for all there exists a u, there exists a k, such that for all v that are initial distribution, the walk converges to a uniform distribution. Yeah. This is okay? This is what we are going to claim. And how we are going to prove it, we are not going to go to the whole proof. We are going to give a sketch. Okay. If your initial distribution, let your v be an initial distribution, okay, and let my pi's be the eigenvectors corresponding to these eigenvalues 1 to n. Okay? Now I can always write a distribution v in terms of some alpha I pi, right? Yeah? Because when I have some eigenvalues and eigenvectors, these are all orthogonal eigenvectors. So you can always, that can form a basis, you can make a basis, and you can always write a distribution in terms of alpha I times pi, right? Now, if I make a walk step on v, what does it look like? I can use linearity, and I can kind of say, this just goes as is that correct? Yeah? I just opened up V, I applied P on Pi, and that is nothing but lambda I Pi. right? Because it's an eigenvector. Now if I, instead of taking one walk step, suppose I took k walk steps, this would only change, right? Nothing else would change, okay? Now if I just open this up, I can decompose this into two parts. I can say this is equal to alpha 1, lambda 1, power k, p1, this is this p, plus the same quantity, this is I greater than equal to 1, but the same quantity. Yeah, that's okay? Yeah. Now, but what is this quantity? With a little bit of calculation, you can show that this alpha 1 itself is 1. That's exercise, you guys can take it. We already showed that lambda 1 was 1 because we kind of showed that the initial distribution, the uniform distribution, was an eigenvector of P with eigenvalue 1, and we have P1 as that uniform distribution U. So this is nothing but the vector U, and this is a quantity that we want to bound. Now just take Pk V minus U, and if we take this L2 norm, these are vectors, if you take the L2 norm, and what you can show, if you want to bound this by some quantity eta, your k has to be greater than log of 1 by eta delta. Yeah.
So why is alpha 1 not dependent on the initial distribution?
No, it is dependent on the initial distribution, but it turns out to be 1.
Okay.
Like, with a little bit of calculation, we can show that actually this decomposition that you have for your V in terms of alpha I times pi.
Oh, we're talking about this specific V where you start at one node, or
No, this happens for any V.
for any V?
Any V, yes. So alpha, like, because this V is any V, but it has to be still a distribution.
Right, okay.
The fact that it is just a distribution, you end up having actually alpha 1 as 1. Yeah? And again, I'm hiding some calculations here. What you can show is there exists a k, that if you want to bound this quantity by some eta, because you want to kind of come as close to this uniform distribution as possible, then you can actually do it by taking k in terms of like log of 1 by eta over delta, okay? And usually we need eta to be some constant, so you can imagine this to be approximately equal to 1 by delta steps, okay? Now analyzing this algorithm again here, so what we saw is, it's possible that I can, in 1 by delta steps of walks, reach to a uniform distribution no matter what distribution I start with, right? So all I need to do is start at some distribution, whatever the algorithm is given. I walk this many steps. Okay, this is approximately, okay? I'm hiding some constant factors. You approximately walk for 1 by delta steps. I'll get there. And once you walk 1 by delta steps, you are in this place where you can now sample a vertex uniformly. Now you repeat this entire process how many times? 1 by epsilon times. Yeah? Now let me label certain things. Let's say the walking cost, for some reason, we will come to it, the walking cost was labeled by some u, or like a different u, it's not the same u, and say the checking step was labeled by some c, then I can perform this entire walk operations in how many steps? I can do it in 1 by epsilon times 1 by delta u plus c. Yeah? And if to start at this distribution V, it took me some cost. It's possible that to start at a distribution, I need to first implement something. That I can put it as a setup cost, and that can be just an initial cost, which is a setup cost, and then you have this cost for your algorithm. Now, quantumly, what we can do is we can actually improve this quantity into another formula, which is almost which looks almost the same, but it has these square root advantages here, And I put a bar here because now it's going to be a quantum algorithm, so the setup might be slightly different, the work might be slightly different, and the other costs are going to be slightly different. Yeah. There was a question.
Yeah. So is there like an easy way to see why we get this logarithm, like of 1 over epsilon?
Ah, I
Because
see.
it was very quickly.
Yeah, I did not do the calculation there. I can give you an easy way to see. So now what happens is, because your delta, okay, so what do you have here? You have that max of delta I for I greater than equal to 2 is equal to 1 minus delta, right? Yeah? Okay. Now what I have is, because the max is equal to that, everything else will be less than that, right? So I can say my lambda I, for all I greater than 2, I have this as less than 1 minus delta. That is okay? Yeah? Okay. Now here, if I just look at this quantity, sorry, this lambda, I can actually upper bound it by 1 minus delta, right? Because I can kind of get rid of lambda I here and bound it upper bound it by 1 minus delta. And I can do that for all I. And that power of k becomes 1 minus delta power of k. But at some point, I'll be taking a square to just, oh yeah, I'll be talking about a square norm. And that kind of becomes 2k, but 2 is not important here. But you see, you have 1 minus delta power of k, and you have something with related to epsilon here. So that's how the log comes, sorry, not epsilon, eta here. That's how the log comes into picture.
You take like a natural logarithm.
Yeah, it's a ln, yeah. So because this will be like like with a little calculation, you'll see that this will be related to something like 1 by eta, or actually this should be this, yeah, greater than 1 by eta. And this is nothing but close to e power k. And then you have, yeah, it's just back of the envelope calculation. We can do it in some time. Yeah?
So physically, what are those eigenvalues of the adjacency matrix?
Yeah, what do you mean physically? Like,
So what are they like? They are just okay, something that we measure per se, and we get between 1 and -1, right? So what do they physically represent in our walk system, or what are they?
wait, right now we are in a classical world. We haven't even come to quantum.
Okay, yeah.
And all it is kind of giving me is not like a like I don't see any physical thing here. All it is giving me is a tool to analyze, like how many times I have to keep walking to almost reach a uniform distribution. So it's like,
So yeah, I mean intuitively, how are they related to the steps that I should take to, let's say,
so okay, as an algorithm perspective, you are at some vertex, so your computer kind of knows which state you are in, and the update step is going to tell you what my neighbors can be in some sense. The update step will take me to another state of the vertex, but the algorithm is only just walking to different neighbors. That's it. But this is just helping me with analysis of how many times I have to keep doing this step to reach this sampling place. Yeah?
Why have you focused on reaching the uniform distribution?
Oh, that is a method. Yes. Okay. I'm not saying this is the only method to find a marked vertex, but this is a method to find a marked vertex, right? Because if you did not need this walking and you could already sample, you would have just done that, right? That is what the first algorithm made you do. But in case you don't know how to sample, because for some reason the graph is given in some other way, then you will need to construct a sampling procedure. And by walking, I'm constructing a sampling procedure to give it to you. Yeah? Yeah.
So we have this, our vector converges to the uniform distribution, but we also have this dummy entry as the first one, which corresponds because we, in the P matrix, we had this first row as just all 1 over D's.
Not
Was
all.
this true?
No, it's not all 1 over D. I was just giving an example of it'll have D points here that will have 1 over D.
Okay.
Like every row will have some D locations which will have 1 over d, because that's the kind of matrix that you're working on. It's a d-regular graph, right? So this is not a dummy entry. It is corresponding to some vertex, like a distribution over some vertex. So it's not a dummy entry. Any other question? Yeah?
Yes, I was wondering, based on the question before,
Yeah.
we were talking about the sampling that, we wanted. I guess I would have intuitively thought we wanted uniform because we don't know which ones are marked. So
Yeah.
I was wondering, because you said this is a method,
Yeah.
like, do we sometimes have more information, like, in general? And then what kind of other distributions,
So for the context of today's lectures, we will not have more information. But I mean, there is possibility that in a graph situation, I actually know, like, I can possibly have like a neighborhood that is like, which promises that, oh, this neighborhood has an element which is in the mark set. So I can have additional structure, right? Then you don't want to do a uniform sampling. You would want to sample something from that neighborhood. Yeah. Yeah. Yeah.
Is there a way we can sample and also keep track of the elements which might be marked because we are going around the neighboring vertices?
Yeah, that's also possible. Like you can always keep track, but at any point you want to kind of minimize the amount of things you're storing also, right? And this procedure is very cost effective from memory point of view, because all you need to remember at any point of time is what vertex I am right now in and how do I get to my neighbor's vertex. That's it, right? So like if I have n number of vertices, then with almost like log n number of bits, I can remember the state of my algorithm. Yeah. But the procedure that you're kind of suggesting would have to make me like a list where I'm storing like, oh, I visited this vertex, it was not marked. So it's kind of like an iterative procedure that you're suggesting. Yeah. Yeah?
So having negative eigenvalues
Mhm.
implies that there are indices which can be negative, right?
No. Say, for example, I give you such a simple matrix like this. This might have a negative eigenvalue, I'm supposing. Does it? Wait, no, this one does. This has? Yeah, it has a negative value. Yes. It's symmetric around 0, yeah. But all the entries are still positive.
Okay, and the entries of the vectors are always positive also.
Yeah, the entries of the vector are always going to be a distribution. So they're going to be not only just positive, they're also going to all sum up to 1. So yes, all this analysis that I talked about only works when this V is a distribution. It cannot be any random vector V. Okay?
So after applying the matrix, I'm getting a new distribution,
Yes.
right?
Yes.
So if I have a vector and the eigenvalue is negative,
Yeah.
I'm getting a new distribution with negative.
No. So this is magically these topics are very well studied in spectral graph theory and these kind of topics. This is just a distribution preserving matrix actually. So what it does is it takes one distribution to another. It keeps doing that. Even though it itself has eigenvalues which are negative, it will never give a negative value to the vector V. Like you can even think of something like this. Like this will be a very valid P matrix. Yeah. Any other questions? No? Okay. Anyone has a time for me? 9:37. Okay. Maybe we take like a 5 minutes break, but you can ask me questions and then I resume with the quantum walk. Yeah. But you have a question, looks like? No? Okay. Yeah. We can do the calculation maybe in the break about the. Yeah? Yeah. Okay. And now let's continue with the quantum part. Okay. So classically, we kind of saw this quantity, right? Yeah. We saw that the cost of a walk algorithm was something like setup plus 1 over epsilon times 1 over delta times u plus c. Now this was the checking cost. This was the cost to take one step of walk. And we were taking about 1 by delta walks, right? And by just doing this procedure, we were coming to this distribution, which was like uniform distribution. So we were kind of doing this sampling procedure here. So that was the cost involved with epsilon. Yeah? Okay. Now here again we have this situation. We have number of elements in the mark set is epsilon times n. Yeah, same. Everything else is same. The graph is deregular and all that same things. Non-bipartite and connected and everything. Okay. Now the way we do quantum walk is we are going to now try to simulate the classical walking thing, but now we are going to walk in superposition. Like that's how we will get these speed ups. Yeah, and the claim speed ups that I'm going to say, what we want to achieve is something like this in quantum is yeah, now you see there is like a square root advantage, right? So that means I will be using square root number of walk steps, square root number of sampling steps and all, okay? Yeah. Now, I'm going to use Bra and Ket notation. I'm mostly going to use Ket notation to kind of denote the state of the algorithm, okay? Now, in the classical algorithm, we were walking on every vertex, right? So what did I say? My classical computer is always going to just remember what is the label of the vertex I am right now at. And when I walk, it's kind of walking to another vertex, and then it is kind of just remembering the label of that vertex. But quantumly, we are going to slightly do something different. Instead of walking on vertices, in some sense, we are going to walk on edges, okay? We are going to store two registers. We are going to have register, the first register stores a label of a vertex in the graph, and the second register is going to store another label of the vertex, but they both together have to be an edge. So we are going to have a state of the algorithm on x and y, where x, comma y actually belong to the edge set E. Yeah? Okay. Now, everybody is familiar with superposition and all those concepts, right? Yeah? Okay, good. Now, let me construct a state which is, say I construct a state U, which is like this. A uniform superposition over all edges. That is what I want to construct, okay? So x in V, x and px, where px itself is just this. Yeah, this is just same. This I'm saying this is same. Are you guys convinced that this is state, quantum state, which is on uniform superposition of all edges of the graph? Is that clear to you all? Yeah? See, I'm going to denote P of x as the uniform superposition of all neighbors of x. Okay? So P of x is a superposition of all neighbors y such that xy belong to this edge set. Okay? And uniform superposition, so I kind of put a amplitude of 1 by root t. Now this is just Px itself. Now I'm going to construct uniform superposition of all vertices, like tensored with their particular neighbors. And if you open this completely up, all you will get is root n times d uniform superposition of x tensor with y. You're going to get just the same, this thing, okay? Yeah. Now, I want to stay back in this kind of notation because it's going to help us a lot later. And I'm going to delete this. This was just to tell you that it is the same. Yeah. Now what we are going to do is we are going to take this state and we are going to what to say, rewrite the state in terms of something called a good state and something called a bad state. So I'm going to write this u in same way. I'm going to say, okay, this is nothing but x belongs to M, where x and px are there, plus, okay, I'm going to use the normalization factor later. There's some normalization factor here, then some normalization factor here, and this is x not in M, x px. Is this fine? Now what did I do? Like the only thing that I did just now is I took the state u, I took the same state u, I just opened up this summation, I grouped all these vertices that are marked into one side and all these vertices that are not marked into the other side. That's all I did, okay? Now this normalized, I'm going to call as the good state because this is the state that we want to search for. We want to search for a marked vertex. And this normalized, I'm going to call a bad state because that is the vertex we want to avoid. Yeah? And because all this is a quantum state, they are all having amplitude square to 1. What you can write this u as is you can write this as some sine theta g plus some cos theta b, such that sine square theta plus cos square theta would give you to 1. And now we are going to improve this amplitude on the good state. We are going to now give a procedure that will boost this sine square theta, this amplitude to a bigger quantity, so that in the end, when you measure this register, you land in a good state. Yeah, that is what the procedure is going to be. Clear? Yeah? Okay. Now I'm going to give you the procedure of how to land in a good state. Okay. Now let's look at this. Suppose we had this subroutine. Okay. Now suppose to our disposal, we had a way to reflect through B, and I'm going to show what reflecting through B looks like, and another procedure that kind of helps us reflect through A. Then can I land into a state which is a good state? This is what I'm trying to do, okay? Now let's have a pictorial depiction of that. This good state and bad state are orthonormal to each other. That is clear, right? Because they don't have any overlap of vertices, so you can like easily see that they are orthonormal. So I can write my bad state here, and I can write my good state here. Then can I say my u vector is something which is making theta with a bad state? Yeah, because look at the u vector. I kind of said u vector can be written as some sine theta times g and some cos theta times b, right? So if this is my sine theta, the projection on the good state is sine theta, and this will be the cos theta. Yeah? Okay. Now what would do I, like, if I can reflect through B, what do I mean? I should be able to, with one step, come here. Yeah? Right? Now I want to reflect through U again. What do I mean? I should be, now this is my current vector. I want to reflect through U. That means I should be able to take 2 theta steps here, right? Yeah? Now see, I started with my vector was initially here. I did one reflection through B. I reached here. This is my step 2. I did another reflection by U. I reached here. This is my step 3, right? Now I continue doing that again. Let's look at this. This vector you want to reflect again by B. You will come somewhere here. Then you want to reflect by U again. You are going to go farther away there, right? So all I want to do is I want to keep repeating this procedure until I kind of reach close to this, right? So I want to do this procedure some k times, and I want to kind of reach the total amount of reflection to become around 90 degrees. That's all I want. And once I kind of reach close to this G, when I measure the register there, the first register there, what will happen? With very high probability, I will land into a register inside G, which is a good state. Yeah? This is good? Okay. Now this procedure, basically, like with one step, like if I'm doing a k-step reflection procedure, in the end of k-step, my state of the algorithm, let's denote it by psi, kind of looks like something like sine of 2k plus 1 theta g plus cos of 2k plus 1 theta b. Okay? Yeah.
Do I measure the state before doing this? I don't, right?
No, no, you don't. No, you don't measure at any point. You only measure after k steps.
Okay.
Yeah.
So what if my initial state was like close to G, to the good state, but I don't know if it's
No,
where it's.
you will know. The reason you will know.
I would have to do it would not be efficient enough.
Yeah, your point is valid that if you don't know the like how many times you need to rotate, you can obviously shoot out and then have to repeat the procedure. But to our advantage, we know the value. We know how many marked elements are there. So we know actually we know how theta looks like for us. And now we just want to make sure that this total quantity, this 2k plus 1 theta, goes near to 90 degrees. Yeah? And we know theta because look at this. This is something I should have. Yeah, okay. So your sine squared, okay, let's kind of look at the amplitude of good state, right? Now, how many elements do you have in your good state? You have about m of them, right? So initially your probability of good state is actually how much? So your sine square theta is almost equal to 1 by just epsilon, right? Yeah, because the number of states that is good is kind of epsilon, right? Okay. Now what I want to say is, can I not say theta is around sine inverse or like arc sine of 1 by root epsilon? Yeah? And which is kind of like if theta is close to 0, we can always say this is almost equal to root epsilon, right? Yeah?
Why do you choose to do reflections instead of rotations, for example?
What do you mean? What is the difference for you?
We are reflecting in B and then reflecting again with the other side to the other side.
Yeah.
Why not applying like a rotation to the vector or something like?
Okay. So I started with a statement where I said, suppose we have this, right? There is a suppose that I still have to fill in. Now suppose we had a procedure that we can reflect about B and can reflect about U, then we can reach this in some k steps, which is very close to 1 by root epsilon, okay? So if you had a procedure which kind of let you just go, that's totally fine. Okay. Now what I'm going to show is I can implement these two procedures. That is what I'm going to show. But you're welcome to rotate it also. Yeah.
What exactly is the difference with Grover search? Because this procedure seems very aligned.
Very nice. Yes. This is exactly what Grover search is doing. In fact, this is like Grover search can be applied to something called amplitude amplification, which is also almost this. So if you have the chance of, like if you have the probability of finding a marked vertex in like which is epsilon, you can classically you would need actually epsilon 1 by epsilon steps, right? That's what we saw. That's a rule of classical what to say analysis. But quantumly you can do it in root epsilon time, and the reason you can do it in root epsilon time is because of this procedure. Yeah.
This might be a stupid question, but like for example, in the graph that you wrote down,
Yeah.
step 2, if you project and let's say it projects along G along this y-axis,
Yeah.
it's going to be a negative value.
That's fine, because see, when you project something, your negative phases are not what kind of. Yeah, it'll like that's totally fine if it even if it gets a negative phase, because you will end up measuring, and the probability is still going to be sine square something. So it's a like we just want to maximize the probability. Right? Any other question till now? But like people who are familiar with Grover's algorithm would already see that it is actually a Grover kind of amplification that we are doing. We are amplifying the probability. Yeah.
I guess I was just wondering, because it's very important, this epsilon, so we don't overshoot.
Yes.
I mean, in general, what if we had a problem where we don't know the epsilon? We're just promised that there is a set, but we don't know how big it is.
There are actually procedures, like I cannot write it on top of my head, but there are procedures where even if you do not know the epsilon value, you can kind of run it a couple more times to get an estimate of what the epsilon value could be, and then run it.
So
that
it boils down to kind of guessing what this epsilon could be, and then.
But smartly guessing. It's not like yeah.
Okay, thank you.
Yeah. But in this case, like, it's very clear what we know epsilon is. So we will we might overshoot somewhere here. That's it. But we will be very close to this G state, so it's going to be fine. Yeah? Now, as I promised, I have to still clarify the suppose part, right? I said, if we had a procedure like this, then we can, in 1 over root epsilon times, almost reach the good state, right? But that relies on me having this procedure. And I'm going to now tell you that, oh, yes, we do have this procedure. But it's going to take a little time. Now, let's see. Yeah. Okay, this is clear, right? Why the k has to be almost 1 by root epsilon? Yeah, because your theta is kind of like this, but you want your theta, your 2k plus 1 theta to become pi by 2, right? You want it to be almost 90 degrees. So you just do a little calculation, constants here and there, but you will get almost 1 by root epsilon steps. Okay, now let me go to implementing these two procedures. Now look at this procedure. Let's look at procedure 1. I'm going to erase this, which is here. It's very hard to keep switching between chalk and pen because my mind doesn't know what to use when. Oh, it rhymed. Okay. Yeah. Okay. Now we are going to reflect through state B. Okay. Now what is state B? And what do you mean by reflection? So when I have some state, when I reflect something, suppose I have a vector, okay? And I kind of split it by, I decompose it to the B part and something to perpendicular to B part. Yeah? When I reflect, the part that is parallel to B just remains without any change in sign. But the component that is perpendicular to B gets a negative sign, right? That is what reflection means. So in some sense, we have to decide when to give a negative sign and when to not to give a negative sign. Now, B is the bad state, right? So anything that has span of bad state, it should just stay like that. And anything that has component of the good state should get a -1 phase. That's what is happening with the reflection, okay? Now, how do I decide what is a good state and what is a bad state? What did I do in the classical step? When I had to decide, is it marked or it is not marked? I had to check, right? And to decide here whether it's a good state or a bad state, all I have to check is this state marked or is it not marked? So this procedure, I have it because that was what was given in the algorithm. I'll get there. So now, for this, I only need the checking cost, right? So to implement this procedure, I only need the checking cost. But because it's a quantum checking cost, I'm going to just put it as a bar C. Yeah? And we will now come to this cost here. Your question?
Yeah, this might be a bit of a dumb question.
That's okay.
So if we're doing these reflections, then it looks like we need to know like in which basis we're working to do these reflections. But
Yeah.
if we know the basis, then we know the good state, right?
So when you want to kind of do these reflections, you don't really need to know the basis per se. You only need to know how the action should be, right? Like, see, for any, like, what do you want when you want to reflect through B? You want that anything that is not marked get a +1 phase. So let me like have my my quantum state. Let me draw a unitary. Just as this, okay? This is a unitary. I'm saying my C is a unitary. Is a okay? Maybe I shouldn't use the word C. Yeah. Let's say I have this unitary C dash, that's the checking reflection. Now what it does is if it is a state X and it takes some other register R, okay, it implements this -1 if X is marked. It basically just does this. You get what I'm doing? Like I have a unitary operation that I define on any vertex X. The unitary operation would just look at X. This is some workspace register R. If my X is marked, it gives a -1 phase. If my X is not marked, it doesn't give a phase. Like, yeah, that's a valid unitary operation because if I do it twice, it just gives me identity, so I can reverse it clearly. Yeah, that's all I'm doing. So now whatever quantum state I am in, whether it is on this G part or B part, my unitary operation is going to act linearly on it, right? Like the linearity of unitary operation is going to make sure that my unitary operation works on this G, it works on this B part. For the G part, it will give me a negative phase. For the B part, it will just keep it same. So that way your angle will start changing. It's, how do I put it? Like, you have to imagine you're in this, like your algorithm is in the state. Your algorithm goes, like your quantum state goes through this unitary operation. And the unitary operation just decides what to do with which part of like superposition it is. It's just acting linearly, that's all. So, okay, so say like if I start with this state, what will be my new state after applying CU? It will become minus sine theta G cos theta B. That's it.
Oh, okay. So it relates to kind of the algorithm being like an oracle. So it kind of it's designed for a specific graph, and therefore it's kind of.
Yeah. Because yes. Because this checking operation depends on, yes, it is in some sense querying the graph about X. Yes, you're right. Yes, yeah. Cool. And yeah, question.
Could you maybe write the part in red with a different color? It's a bit hard to read.
Not red, you mean?
Not the red part. If you could write it again in a different color.
Just don't write with red.
Oh, just don't write with red. Okay, yes, I will, yes. Okay, so this step 1 is clear, that we are able to reflect through B, okay? Now we are going to try and implement reflecting through U, and that is going to be a very tricky part, okay? So for that, I need to, again, describe something. Let me delete this part, okay? Okay. Let me see. Oh, wow. does reflecting through something mean? Like I said, for every state that is span of that U, I will give a +1 phase, meaning I'm not doing anything. And for everything that has like perpendicular, like if it is perpendicular to U, then you kind of want to give a negative phase, right? Okay, -1 phase. Now imagine I actually do this, okay? Now, let me say suppose I have this unitary to my disposal. I will call it as UX. Yeah, these are the two unitary operations that I have, okay? And I'm saying, suppose my graph gives me the way to do it. Just like how we did the checking cost, like you ask something to the graph about how whether it is a marked vertex or not marked vertex. Similarly, in some Oracle query to the graph, you're able to actually take X, take an initial state 0, and you're able to construct this superposition of X with all its neighbors, okay? And this unitary, Uy, is doing something opposite. It is taking 0 on the first register, y on the second register, and it is just constructing the superposition of all y's neighbor in the first state. That's fine, right? It is, you just do this and then you do swap, it will work out the exact same way. Yeah? This is okay? These seem like valid unitary operations that I should be able to implement given that I know something from the graph, okay? Now, imagine I have a subspace A that is span of X and Px. And what do I mean by span? It is just some linear combination of all these vectors in this space. And my subspace B is, say, span of Py, Y. Yeah? Okay? These are the two subspaces that I'm defining. Now imagine I have a reflection that I want to implement about this subspace A, and I want to implement another reflection about subspace B. Okay? If I'm able to implement these two reflections, then I claim that I will be able to reflect through U. And let me show you how I implement this. Wait, I need a working pen. Okay. Yeah. Now, to reflect about subspace A, what I'm going to do, see, I want to reflect about subspace A. What do I mean? Like if something is in span of these vectors, then it should get no phase, right? Now, and if it is not in the span of that vector, it should get a -1 phase, right? Okay. So let me tell you, like suppose I give you a state, come on. This is,
Maybe continue with chalk.
yeah, now my worry is that I'm going to use this space as well. So I'm trying to see if I can, yeah, okay.
I think they are trying to bring some new pens, maybe.
Yeah, okay, till then I can maybe give it in chalk. Yeah, so I want to kind of implement these two reflections, right? Now, what if I use Ux inverse? What if that is my unitary that I first use, Ux inverse. So if I have a state psi which is in the subspace of X and Px, if I apply Ux inverse, what will happen? It will get me to the state Xn 0, right? If it is in the subspace. So all I need to check is, I will apply first, like I will give a state psi into one, like a group of unitaries, and I'm going to give a phase -1 or 1, we'll see, but let's see. So it is plus or -1 phase with psi, okay? But what I'm going to do in this unitary is first I'm going to do ux inverse, okay? The ux inverse, if it was in the span of, if it was in the subspace A, would then give me this state. Because ux does this, ux inverse just give me this. Now I check if my second register is 0 or not. Is second register 0 or 1 or something else, like doesn't matter, but is it 0? If it is 0, then I do ux again, okay? Then I get back again this, right? If it is 0, you would get ux again. Sorry, xpx again. So you got a +1 phase. If it is not 0, you kind of check the second register, it was not 0, so you don't give a phase, and then you do ux again. So you end up getting a, sorry, you give a -1 phase, and you end up getting a -1 phase. You see what I did? I just took this unitary, I applied the inverse of it first, I checked the second register, I saw if it is 0, I did not give a phase. If it was anything non-0, I gave a -1 phase, and then I uncomputed that ux inverse, which kind of gave me this state. Yeah.
So I'm a bit confused because we've defined UX as working on like a larger Hilbert space than, okay, we're gonna check if it's 0, right? So I think we're gonna do a measurement.
When I mean this 0, it is not single 0. It is like all initial states that can, like, it's like logarithmic number of, oh, thank you. Yes, yes. Like when I mean a 0 here, it's not exactly 1 qubit 0, it's like many zeros.
Okay, but if so it would be like multiple qubits then.
Yeah, it's multiple qubits.
Okay, but still if we measure then one of them.
No, then you measure the whole set. Like you just meant, okay, suppose this is like m qubits. Yeah? You measure all the m qubits. Are all the m qubits 0 or not? If it is 0, then you don't give a phase. If it is not 0, then you?
Yeah, but if it's not 0,
Yeah.
you apply UX, right? But UX is...
No. UX you apply anyways. See, you are doing 2 steps here. You're first doing a UX inverse. You are then doing this checking 0 or not. Checking 0. And then you're doing UX again.
Yeah, so what I'm asking is like, I think UX is defined on a larger Hilbert space than UX inverse is defined on a larger Hilbert space than UX right now, because we're checking for 0 in between, but then you're...
Okay. So you want to kind of like include, like you want to kind of say this is a little bigger space? Is that what you want to say? Okay, UX, okay, if this was taking m qubits and this was taking m qubits, UX is working on 2 m qubits and giving me a state also in 2 m qubits. And UX inverse is also going to do exactly that. Like, because your quantum algorithm is always in this x comma some y. Like, yeah, but see, that measurement you can even postpone. There are some technicalities where you don't really, like in principle you are measuring, but you don't really have to measure. You can just like control on it, like a C0 operation. So, okay, this is for simplicity's sake, I said like you're measuring, but what you're actually doing is you're, in some sense, on the second register, controlling whether or not you'll give a phase, like a C0 gate, and that controlling is happening by based on all the values in your second register. So it's a big like set of zeros, not just single 0. And then you're again uncomputing what you had done. So you're uncomputing UX inverse, which is UX. So yeah. With the way I have defined, yes, like because I'm not even defined on how it should behave on the other subspace. So yeah, in this way you can, like, there's nothing wrong. But usually when you're defining, you have, like when you write formal definitions, you have to also say that on other bases, like on other states like this, which are not x and 0 and not x and px, it behaves identity or something. Yes. Okay. Yeah.
When we apply the inverse of UX, do we find back the 0 only if the state psi belongs to the subspace A?
Yes, yes.
Just the case? Okay.
Yes, that's the only case. Yes, exactly. See, yes, this is very important. Because UX is a unitary operation, there will not be another state here that would come from this state. It has to be a reversible procedure. So there will be a unique x0 state for every x px. So you know that if you are seeing second register as a set of zeros, then you know that it is actually a state in the span. Now you do similar thing for reflection around this subspace B. Just the same argument. It's just that instead of checking the second register for 0, now you check for the first register for 0. Yeah? Okay? Now what this step kind of did is it reflected about B, and so what we have implemented now is a reflection about subspace B and a reflection about subspace A. And now what we can say is you can now construct a unitary operation parameterized by P. P is the same matrix that we had before, like the distribution stochastic matrix that we started with. But I will show you why we are parameterizing this with P. And this can be just written as some reflection of B times reflection of A. So this matrix itself is just the matrices that implemented this and the matrices that implemented this. Okay? And the reason we are going to use this unitary operation will be clear soon. Okay? Because what we are trying to achieve is actually that we want to reflect through U, right? And to reflect through U, we are going to use this unitary, but that's not going to be direct. We are going to still do some more procedure to reflect through U. Okay? Yeah.
Just to clarify, we're saying that you are in that subspace,
Yeah.
only then you're able to reflect through you. Is that?
No. So we are going to say that for elements that are in this subspace, this is how it's going to behave. For other elements, we don't have control on how this UX behaves, but we are going to use the fact that the way UX behaves gives us this 0 and UI respectively for this 0. Yeah. Any questions until now? No? Okay. Now, I have to still tell you how to reflect through U, right? Because we did reflection through B. Once we have done with reflection through U, we are done with the quantum algorithm, okay? So bear with me. Now, the way I'm going to reflect through U is by looking at the eigenvalue of U for this matrix WP. That's a tricky part, but we are going to now kind of understand the eigenvalue of this matrix. This is a matrix, right? This is a unitary operation. It is just a product of bunch of unitaries. So this is going to be a matrix. It's going to have some spectrum. Now we are going to see, is U, first of all, an eigenvector of this matrix? If it is, then what is the eigenvalue? Then what we can do is, by kind of looking at the eigenvalue, we can then decide, whether we should reflect or whether we should not reflect. Okay? Now let me bring your notice to another procedure called a phase estimation procedure that is very common in quantum computing. Have you guys heard of phase estimation procedure before? Yeah, phase estimation. Yes. Okay. So now we're going to use phase estimation. Now what phase estimation tells us is, suppose I have a unitary. Suppose there's a unitary B, okay? And this B can be decomposed into its eigenvalues, e power I theta 1, and its basis, B1. Yeah. Suppose I have this unitary operation. Now suppose I can decompose this unitary matrix into its eigenvectors and eigenvalues. I will kind of get this kind of a quantity, okay, for all particular eigenvalues I equal to 1 to n, if this was a n dimension matrix. Okay? Now, because B is a unitary matrix, you're going to be promised that all its eigenvalues are going to be of the form e power some I theta. Yeah? Okay? So all the eigenvalues, lambda I, was it lambda? Yes, lambda I is e power I some theta I. Oh, this I is this imaginary number I, okay? Or let me put this as j so that we don't have confusion. Let the index be j. Okay, now let me first prove that for this U and for this matrix WP, U is an eigenvector of WP with the eigenvalue 1. Okay, now what is U? U has superposition of all edges, right? It is having all the vertices x and its neighbors. Okay, isn't it very clear that this U is already in span of this is in subspace A? That's kind of clear, right? Okay. Now it's also clear that this U will be in span of this space, subspace. Like it's also in this subspace. It's just rewriting, but it is the same edges set. Yeah? Now, so if U is in this subspace and in this subspace, reflecting about these subspaces will not add any phase, right? So what you're going to get, you just send U through this unitary WP, you're going to get out U with just 1. So this WP times this vector U gives me 1 times the vector U. So clearly U is an eigenvector with eigenvalue 1. Okay? Now eigenvalue 1 in this kind of picture just means your theta is 0. Very good? Yeah? So lambda equals to 1 implies the corresponding theta is 0. Okay? Now there is a quantum procedure called phase estimation where if you have some unitary B and you are given some eigenvector psi, which is an eigenvector of this matrix B, then I can estimate the eigenvalue theta corresponding to that vector. So that is a procedure called phase estimation procedure. But the cost of the algorithm kind of depends on the precision of theta value that I want to attain. If I want, because theta is like a real number, right? It can be of arbitrary precision. So, but if my quantum algorithms are truncated, like it's going to run only for a finite number of steps. So if I run for a finite number of steps, I'm only going to achieve some precision. So this phase estimation procedure kind of estimates this theta value to some precision. And what this helps us is, now because we have this unitary operation WP, and this unitary operation, if we kind of see what how the way it was constructed, it was in some sense taking 2 walk steps, right, for each reflection. Remember, at one time we were doing UX inverse, we were checking something and it was doing UX, and for this reflection it was doing UY inverse, you were checking something and you were doing again UY. So in some sense this entire procedure was walking like 4 steps in superposition. And because of the structure of the graph, this WP ends up having its first lambda value 1, and the second lambda value is little far away from 1. Like it's kind of little far away from 1. And how far is the quantity depending on some function of this delta. What is this delta? The spectral gap that we discussed in the classical setup. Like it's the same delta, it just comes into the picture in this kind of way. So now what we are going to do, we are going to now run this phase estimation procedure by seeing this as a unitary operation, this as a vector, and we are going to estimate what its eigenvalue is going to be. Now if its eigenvalue comes out to be 0 with some precision, then I'm going to say don't add any phase. If it comes out to be some like 0 point something something, right? If it comes out 0 point something something 1, then I know it is not 0, then I'm going to give a -1 phase. So this is how I end up reflecting through this U. And the cost is going to become the precision that I care for, and the precision kind of depends on this spectral gap. So there, the number of times I have to run this walk operator ends up being 1 by root delta. So to get a precision of delta, I think I need to run it to 1 by root delta. And what was this operation doing? Kind of like doing 4 walk steps, right? So I know that I can reflect through u by using around 1 by root delta times some work cost u. So now if I combine the whole procedure, I have again come up to this situation where I am going to have a 1 by root epsilon. That was because of this the total reflection, that good state, bad state thing that we did. And inside we are going to have like 1 by root delta and plus this C cost because of this reflection through B. And you end up getting this cost in the quantum setting. And this extra setup cost comes if you want to kind of also acknowledge the time, like the resources you spend to start at a particular vertex or at a particular distribution. So this is how we achieve this cost as opposed to the quadratically worse factors involved in the classical setup. Yeah? Cool? Is it time for the big break now? Oh, okay, perfect. Okay. So after, like, so now we have kind of finished, I think, can I, we have finished part 1, and this quantum walk framework is called MNRS framework. And I would suggest see Ronald DeWolf's lecture notes. They are amazing, and they have every detail calculated very well. Exercises also. Yeah. Yeah, I'll write on the name. Yeah. And this is part 1 that we discussed, okay? I'm going to write the lecture notes. Name. Yeah? Okay. Yeah. Any questions? What?
Why state U
Yeah.
in the subspace B?
Oh, yeah. Okay. Yes. I'll just show you. See, what is subspace B saying? Subspace B is just like all neighbors of Y in uniform superposition. Because it's only because they are both uniform superpositions that they both have one common, I mean, at least one common element, that is U. Yeah. So, yeah.
When we first define the space,
Yeah.
or our state, it's like X, the tensor Y.
Yeah. Yeah.
Tensor product. So everything that we are working in lies in the E, tensor product E, right? Because X and Y both belong to this space.
What is E? Your edges?
Yeah, I mean, that's what you wrote, like X, Y, they all both belong in E,
Yeah.
this space, right?
This is the set of edges. Yeah.
But in which space are we working in?
So we are still working on like vertices, space of vertices, but instead of having the space of vertex, like one vertex, we are working with that vertex and its neighbors. Like,
Why don't we take like 3 or 4 or infinite?
I mean, you're allowed. You're allowed to take like different, combinations. Yes.
X, Y, Z.
You're allowed. I'm just kind of giving one algorithm that is achieving this cost. Like, yeah.
So why is not random here? Why is the set of neighbors of X?
Yes. Why is not random here?
Yeah, I know, but why don't I take like neighbors and then the neighbors?
Yeah, you can do. See, if your algorithm can, like, see, the whole point of coming up with an algorithm is we want to optimize the cost, right? If your algorithm is taking more cost, then maybe your algorithm is not a good algorithm. But if it is beating this cost for a certain task, then why not? Like, you're very welcome to take it. Yeah.
Is it done? Like, is it done?
Yeah. So people have come up with different parameterizations of these. There are algorithms which don't do so many walk steps, but do walk and check simultaneously. So then this 1 by root delta comes out. Now, in some sense, that is beneficial. Like, this is beneficial when the checking cost turns out to be very costly. Then you don't want to check all the time. You want to walk for some time and then check. But if it is not that costly, if it is almost comparable to you, then why not check? So yeah, you can modify these algorithms any way you like, but ultimately you want to achieve the optimized value. So, yeah. Yes. To recap, we had this quantum walk algorithm, and with the complexity of setup plus this 1 by root epsilon that depended on this number of marked vertices, this delta came into picture. That was actually the spectral graph, a spectral gap of this particular graph that we were working on, you see. And then you had this update cost, which is like walking to a neighbor, but quantum walking, okay? You're not like really walking to one neighbor, you're walking in superposition. And then you had this checking cost, that was checking whether a particular vertex was marked or not, okay? And now we are going to use this kind of a walk algorithm to actually solve another computational problem that has no relation with a graph. The computational problem will be a very simple computational problem, but we are going to use this kind of a framework to now give an algorithm for that particular computational problem, okay? Now for that, I'm going to first introduce something called a Johnson graph. That is not the computation problem. I'm going to describe a graph to you, and then we're going to use that to solve something else. Okay? Now, Johnson graph is a very interesting graph. You will see soon. Now, I forgot if it is Johnson's graph or Johnson graph. Forgive me for dropping an S. Okay? Now, this graph is basically parameterized by two quantities, n and r. Okay? And we write it by jn. Now, the way the graph looks like is every vertex in this graph is actually an R-sized subset of this set N. I will repeat. So each of these vertices in this graph actually contains R-sized subsets of elements from 1 to N. So how many vertices are there in this graph? Sorry? Need not be. Like they are all different R-size subsets. So it's possible that two subsets have some common elements. But how many R-size subsets can I make out of elements from 1 to N? N choose R? Yeah? So the number of vertices in my graph, so my graph is this Johnson graph, right? The number of vertices in my graph is going to be N choose R. Do you guys denote it like this? I denote it like this. Sorry? Yeah? Okay. Now the way we are going to give... you have a question? No? Okay. Now I kind of described the vertex set to you. Now I'm going to give you some edges, okay? The way I'm going to connect any two vertices, if S and like vertex labeled by S and S dash belong to this edge set E in this Johnson graph, if and only if S intersection S dash is equal to R minus 1. Now what do I mean by that? All I'm saying is I connect two vertices of this Johnson graph only if they have exactly one element not same and everything else is same. So they should agree on R minus 1 elements and only one element they should not have same. Then I put an edge. Okay? Now, can I argue that this Johnson graph is a D-regular graph for some value D? Can we say that? Yeah? Because now see, fix a subset S, right? How many neighbors will I have for S if I fix the edge condition this way? That's a question. Yeah. How many neighbors? So I have this set, like every vertex is a subset in this index set 1 to N, and size of every vertex is just R, right? And I'm connected to my neighbor only if they differ exactly with one element, right? So can I say my vertex S will have first of all, it'll have at least R neighbors.
No.
At least, there are more. Yeah. Yeah, it'll have at least R neighbors. How? I can take every element in S to kind of replace to get R different elements. But that to replace every element itself, I can choose from how many different values? N minus R values, right? Because I have N minus R values to choose from. So in total, I will have R times N minus R neighbors for every vertex in this graph. Okay? So my D regularity here, my D is basically this R times N minus R. Let me just confirm. Because the spectral gap is going to be in picture. Yeah, it is R times N minus R. And now, for this kind of graphs, yeah, go ahead.
So we have the R minus 1 because we have no self loops, or why is there a minus 1?
No. We kind of want to enforce that two vertices are only connected if they represent two different R size subsets, but only one element in their subset is differing. Like, suppose I kind of have a graph that is, say, of like Johnson graph of value, say 4 times 2, suppose. So I'm kind of constructing all two size subsets from elements from 1 to 4, right? So one element will be 1, 2. This is a subset, 1, 3, 1, 4, and then I have 2, 3. So all two size subsets I make. Now these vertex will be only connected if they only differ exactly in one element. That is how I'm enforcing the edge set.
They should overlap in only 1 point, basically.
No, they should overlap in R minus 1 points. They should differ only with one element. Okay, the 2 example is bad because it's kind of symmetric around that. They should basically be common with R minus 1 elements, and they should differ in exactly one element. Okay? Yeah, this graph is like a combinatorial nice object, and it happens to have its spectral gap value close to N by R N minus R, which is almost equal to 1 by R. Okay. So the graphs, this capital N, sorry. This is, sorry, 1 second. Yeah, tell me.
Why did you approximate it? Is N really bigger than R?
So usually N and R are going to be polynomially related for us. Like we are going to choose it in polynomial. But I'm going to approximate to make analysis simpler.
For me, when I look at it, I realize that N is very much greater than R. So you can neglect N with respect to R, and then you can have approximation 1 over R.
Yeah. It is going to be much greater than R. So if your R is going to be kind of like some N power beta is what we will choose for a beta value strictly less than 1 and greater than 0. So we will make it polynomially related, but yes, your N will be much greater than R that way. Yeah, in that sense. Is a Johnson graph setup clear? Yeah? And like this is important for us. What we kind of have here is that the delta, the spectral gap of this graph, like this is a graph which is very nice structure, and it happens to have the spectral gap as 1 by R. Okay? Yeah.
Just to get some more intuition.
Yeah.
Can you give us some example of like some real application of this?
Yes, exactly. I'm going to now use this Johnson graph on a computational problem that will not have anything to do with graph, but we are going to solve it. Yeah? Okay. This much is clear, right? Okay. Now,
Just D. Can you repeat what is D exactly?
so the D, remember we only discussed like this result was applicable for D regular graphs, which means every vertex in this graph will have exactly D neighbors, not more, not less. And I argued that because I am kind of enforcing that my neighbors are only connected with this condition, that makes me have D this value. Yeah? Okay. Now let me give you an example where we can use this amazing Johnson graph and come up with nice complexity using this walk on a Johnson graph to solve something completely different. Okay? Now the problem that I'm going to describe is called element distinctness problem. Okay? It's a very, very simple problem. Shoot. Yeah. And the problem setup is quite simple. You have, that's n I wrote, right? X1, X2. Teachers. Yeah. Okay. So the setup of this question, this is called element distinctness problem. You are given capital N integers. Okay. The integers can be values from some universe U, which is a set of integers. Now the task is to output whether there exist two different indices but with the same value. Okay? And the additional promise that we will have, additional promise, either there exists exactly one pair ij of this condition, okay, or no pair at all. Okay, so I am given an input of n different integers. Either all my integers in that input are distinct, or they will have exactly one pair xi and xj of different indices I and j that have the same value. Okay, so if my input was say 1, 5, 6, 9, 10, then it is a no instance because it doesn't have any same value. But if my input was say 1, 5, 6, 6, 9, then this is a yes instance because I have two different indices with the same integer value. Yeah? Okay, this is the setup. And I want to kind of solve this question. And the cost, like the resource that I'm going to use is I'm going to ask very few questions to my what is xi. Like if I give an input I, like tell me what is x5. That is a question that I will ask the oracle, okay, the input oracle. I want to minimize that and I want to solve this problem. Because see, if I ask what is x1, what is x2, what is x3, what is x4, what is x5, if I ask for all the n's whatever xi was, then I can solve it. So I know how to solve it if I can ask n times this question. But I want to do something smarter because I have quantum power, why not use it? Okay? Now I'm going to exhibit a quantum protocol which can solve this in n power 2/3 queries. Not even like linear in n. See, not like constant saving off. It's actually a polynomial save of like n power 2/3 number of queries. And the cool part is that you cannot do anything beyond n power 2/3 queries for this problem. That was a result proven by Xi. That was a separate result which argued that if you have quantum access to these queries, you will still need n power 2/3 queries to solve this problem. So in some sense, the algorithm that I'm going to give you is one of the best algorithms because it achieves the exact bound. Yeah? Okay. Now the way we are going to do this is this way. Can I erase all these except for this fact that we are going to use this quantity later? Yeah? I'll erase all these other things. Okay. So now I'm going to solve this element distinctness problem on a Johnson graph in a different way. Now imagine I don't want to solve this like if there was a way that I could actually not consider the entire list of integers x1 up to xn, but I could take, some r size subset, which is where r is strictly less than n, and somehow if I can only check on those r size subsets, I might have some speed up. Like if there was some way I can do that, then I might use solving element distinctness not on the entire one x1 up to xn, but I will smartly run element distinctness problem on smaller subsets, and then I will try to see if I can combine solutions of these smaller subsets and find if the yes instance is there or the no instance is there. Yes, that's what we're going to try and do. Okay. Now imagine I kind of construct this Johnson graph on these inputs that are given to me. So I have my input x1 up to xn, but I'm going to now construct a Johnson graph which kind of for every vertex is going to store a subset of my elements from xn up to xn, x1 up to xn. So my subset will be a subset in n, which is of size r. Okay. What it is going to store here is x subscripted by subset s, which means this x will be set all xi's such that I is contained in your S. You understand what I'm doing here? I'm going to now create a graph whose vertices are labeled by subset of size R, which are just subsets of these elements. Yeah, that is what I'm going to do. Now, imagine I was in a yes instance. Suppose I was in a yes instance. I know that there's a promise that if I have a yes instance, there will be exactly one pair that will be a collision pair, right? So if I construct subsets in this way, how many vertices in this graph I will have this collision pair then? Like what I'm doing is, my vertices are just R size subsets of my inputs. That's clear? Okay. Now, if I'm telling you, I'm promising that my input has exactly one collision. If my input has exactly one collision, meaning there is some I and j that exist in this list that has exactly one collision. Now I want to know how many of these vertices in my Johnson graph will have that collision. That's a question I'm asking, right? Like we have n choose r vertices here. Some of them are going to have that collision. Some of them are not going to have the collision. And I kind of want to know how many of them will have the collision and how many will not have the collision. Yeah? Shall we calculate? Okay. Now imagine if a vertex has that collision, then it should have I and j together, right? Yes, because that I and j have to be there in the vertex set, only then I can have the collision. Now if I fix that I has to be there and that j has to be there, how many other elements can I choose? Exactly. So the total number of vertices that I will have this I and j are going to be n choose r minus 2. Clear? And this is going to be my marked set. So I'm going to now mark a vertex as a marked element if it contains that I and j. If this is contained in I and j, I will just mark it. Okay? Yeah? So my value of m is going to be n choose r minus 2. And my n on this graph, so that is n dash, because the number of vertices in this graph was n choose r, right? So the epsilon that we were using for that particular graph search before will be how much? Around this, right? N choose r minus 2 divided by n choose r. This will be approximately 1 by, sorry, yeah, Yeah, if you just open up the calculation, you will get that it is approximately 1 by r squared. Yeah.
Sorry, I didn't get what determines whether where we find a pair of xi equal to xj in one set or not. Is it random, or what determines if we find it there or not?
Wait, 1 second. I need
It's
to.
already existing. Should exist at least one pair. And then you construct the others. So she's imposing the promise.
So what I'm doing is, I am giving this additional promise, right? I'm saying this, that if there is a pair, there'll be exactly one pair. And because I'm saying there'll be exactly one pair, I know that there'll be exactly this many elements that will be marked. Okay? And if in a situation, there was no one instance, that is like there was no indices that were at the common value, then no element in my Johnson graph will be marked. Yeah? So now my task has started from actually solving this problem, but I will not solve this problem directly. I will solve it in this Johnson graph setting, and now I will distinguish whether I have a graph which has one marked vertex or not, versus not one marked vertex, but this many marked vertex, versus no marked vertices at all. You see what I have done? Like, I took a problem, which is a computational problem. I mapped it into a Johnson graph setup. Now I'm going to use my quantum walk algorithm that had these nice properties on this Johnson graph to solve this element distinctness problem. That's what I'm going to do. Yeah.
So if it has no marked points, epsilon is 0. So what happens to the complexity there then?
So no. So this kind of is like a upper bound on, like, when there is mark point, what is the epsilon value? So it's kind of going to distinguish when there's a mark point versus no mark point. Yeah. So okay. Now we are going to plug in these values that we got from the Johnson graph into this formula here, and we'll achieve this n power 2/3 thing. Yeah. Okay.
If I'm getting this correct, we
Yeah.
are putting the elements which are same in the same set of a Johnson graph, right?
No, we are going to construct every possible R-sized vertex set from all these elements. So all the R-sized vertices, like subsets of these elements, will be there. What we are going to do is, in principle, we will say something is marked if it contains the answer. Both xi and xj. Yeah. And we know, like, because it will be only marked if it contains both xi and xj. And we know that there is exactly one xi and xj. We know that there will be like m of them that are marked. So, yeah? Okay. Okay. Now let me plug in the values and kind of see what happens. Yes. This is a good place. Okay. So now setup cost. So remember, in Johnson graph, what did like in my graph algorithm, what is the thing that I had to set up? I had to set up for every x in my in my graph. I had to set up a superposition of. Oh, you have a question first?
Yeah, I was just wondering, so we mark it if it contains xi and xj, right?
Mm-hmm.
But what if one of them contains, for example, xi and the other contains xj?
Then it's not marked. That's not marked. Yeah.
There's no marking.
No, there's no marking. Only if the entire set, like entire vertex, contains both the pairs, then I will mark it.
And is there any way to know, like, so we kind of make these subsets, but so it would be nice to kind of like make these subsets knowing that one of them will contain both, right? Because otherwise you
No, so we are not going to make the subset anyway. Like I'm going to walk on this graph, right? So my algorithm is going to kind of keep evolving its subset identity in some sense.
okay, so if it doesn't find anything, it just changes.
Changes, yes, exactly. It will change one element. Yes, that's exactly what it's going to do. So I will start at an initial state, right? In my original walk algorithm, what did I do? I started with a uniform superposition of all my vertex with their neighbors. I did that, right? So here also, I will start with all, like each of my vertex will be like storing R size subset along with its neighbors, which are also storing R size subsets, okay? So now to set this up, I kind of need 2R cost because I'm kind of storing R size subsets and R size subsets. And I'm going to do that in superposition. The superposition part doesn't cost me, but the fact that I'm going to store 2 vertices of that big set sizes, I will need 2R cost. So in this case, my setup becomes almost 2R. Okay, when I say it's going to be this cost, I'm almost I'm saying it's almost 2R. Now, what is my walking going to look like? Remember, what did we do when we tried to walk in the original algorithm? We said the walk was kind of taking your x with your 0 to x and a superposition of all your neighbors of x. That was like one step of walk. And the other step of walk was something slightly similar but little opposite, that is py and y. This were like my walk steps, right? Yeah? Now in this case, if I'm on a vertex S and I want to go to my neighbor, like all neighbor, say first I want to try just one neighbor, what will I change? I will only have to change exactly one element, right? Because the only way the edges were connected is if they had their r minus 1 elements exactly the same. So only with one element, I will be able to go to my neighbor, right? So my walk step here cost me just one element change. Yeah, so the cost of walk u is approximately 4 because we have 4 such walk steps. Now the checking cost. Now imagine, I told you like earlier in that algorithm, we were asking the graph, oh, is my vertex marked or not, right? In this case, how can I check if it is marked or not? I can go through all elements inside it. Like your question, right? Like if I knew that your xi and xj will be there, why can't I just start with that vertex set? I'm not doing that. I start with some vertex set, but I can check if they are there or not. So I check for all elements inside my vertex if there is a pair xi and xj that are same or not. And that I can do in R steps if I store them properly. Okay, if I store them in a nice order, if I store them in ascending order, I can check like, yeah, xi and xj, they are side by side, but they are different index, they are there. So that would take me then cost of R. Now let's plug it in. So when we plug all these values, we get like R, okay, I'm removing the constant factors, okay. We get almost like R plus 1 by root epsilon, and root epsilon was this, right? Because root epsilon was kind of like almost like the fraction of marked elements. So epsilon is 1 by R square, so root epsilon will be R. And then I have 1 by root delta. Now my delta was 1 by r, so 1 by root delta will be root r. Yeah? So I kind of put this root r here. My update was around 4, so I can just ignore. And my checking was again r. Yeah? It's all good. Now, I will say, but you know, I really don't need to use any more checking cost. The reason, because we are looking at a query complexity model, in the setup itself, I already stored all my x1 up to xr values, right? Like all the values I kind of loaded in the setup stage itself. So I'm going to just remember that and not keep asking the graph, oh, what is my x5? What is my x6? So I'm going to just use the fact that I already did that in setup. I can always not just use R, I can use 0 cost. So now the term that I have, oh, there has to be somewhere an n. Where did I miss an n? I'm missing an n somewhere. Let me just see. Oh, yeah, maybe, yeah, it's n, I think 1 over. Sorry, epsilon is r by n. This is opposite. n square by r square. Yeah, it's not 1 by r square, it's n square. Yeah, if you just calculate carefully, not like how I did earlier, you will actually get n square by r square. So your epsilon is actually r by n. Yeah? Okay? Yeah. So now the terms that you end up having, you have like r and you have r power 3 by 2 by n, right? And to kind of like make it, am I doing it all correct? Wait.
Shouldn't epsilon be r squared over n squared?
No, there's one over radical epsilon.
Yeah, there is 1 by root of that because we are doing root of epsilon. And this is r, so this is 3 by 2. And I kind of want to balance this, so I get n is equal to r. Oh, 1 by 2 is not good. No, I'm making a mistake with the delta somewhere.
Delta here you approximated 1 over r.
Your delta is 1 over r.
What is the missing?
Yeah, I'm kind of checking. N by root r. Why are they getting n by root r? Ah, shit. Yeah, sorry. This is, okay, this was n by r. Yes. Yeah. Yeah. Okay.
1 over epsilon.
Yes. Epsilon was n squared by r square. So 1 over epsilon was, sorry, this was different, no? Epsilon was r square by n square. 1 over epsilon would be n by r. Yes. Yeah, now do I have it correct? Yes. Okay. Yeah, good. Yes. So, yes, now kind of opening this up, we get like the terms as n by root r here and something 0, right? Okay. Now, what is the choice of r that I can make? Now, r has to be a subset strictly less than n, right? I want to balance this cause. See, if I choose r to be very big, then this term will dominate. If I choose r to be very small, then this term will dominate. So I want to choose an r that kind of maximizes, like kind of minimizes both the terms, right? Yeah? Question? Yes. Now we will see why it works, because you want to kind of have this almost equal to n by root r. You want to choose the size of r in such a way that it is almost equal to this. So you get r 3 by 2 is n. So you need to choose r as n power 2/3. Yeah? Cool? So now, yeah, question.
Sorry, getting back to the size of the marked set,
Mhm.
shouldn't it be n minus 2? Choose r minus 2 because we have our.
Oh, yeah. Yes. You're already fixed, yes. Yeah. Yeah. But the approximation calculation, that's why I was missing n square before. Remember, I had approximated it to 1 by r square, but I was missing it because it's actually n minus 2. You're right. Yeah. Okay? Yeah.
Can you explain by, so it means that in order to know you have to change this one element,
Mm-hmm.
but why 4?
Oh, the 4, because kind of like this this u as this walk step that we had taken like 4 walk steps, right? We were doing ux inverse. Actually, we were doing ux inverse, ux. You were doing a uy inverse, uy. Each of them were actually like 1 walk step in my head. So I kind of took it as 4. Yeah. So now you see, like what I tried to show here is we took a problem that is so different. It has no graph structure, nothing. It's not even a graph question. Now you kind of embedded that as a graph problem. And because that particular graph, the Johnson graph, has such nice spectral properties and this deregularity and all those, we could use that walking on that graph to get such a nice lower bound. Better than actually a simple algorithm that would just check everything one by one. So it is beneficial to still have quantum walks in many setup, and this was one example. So this algorithm was first given by Ambainis. Like the algorithm doesn't go exactly like this. It was the first time he gave a walk algorithm, so it was much more complicated. But a lot of other work started improving on that algorithm, and the presentation that we saw was actually a framework. So you just don't use this algorithm for element distinctness, but you can use this MNRS framework to solve other kind of computational problems as well. So this is one of the result. Let me see how much time I have. Oh yeah, I can go on, right? Yeah. So now, what I kind of discussed in some sense was the query cost of solving this problem, right? Like, if the resource that you were using is to minimize how many times you want to ask your graph, is it the answer or not, or is it, in this case, is it my what is the value of my x1 or xj or not? If this was the resource I wanted to minimize, I got n power 2/3. Okay, but if in case that was not the resource that I want to minimize, but the resource that I want to minimize is the cost of the complete algorithm, everything, like the unitaries that I make, the checking, everything, like the total count of gates, then I have to also update my setup and update and checking cost as those costs, like the running cost of those algorithms. Now for element distinctness, because the problem has some nice structure, you can actually use this same algorithm with a little modification and get this cost. You can get this cost of n 2/3, but with polylogarithmic factors. So for element distinctness, the time complexity, like the Q time, is like some n 2/3 times some log n power some 4 or something, or 2. I forgot the exact polynomial, but you can basically achieve the same time complexity, but with a polylogarithmic factor. Mostly people, like, for theoretical sense, you kind of don't care if there is log factor, but that becomes important if you want to kind of talk about actual implementation, because even then that's a overhead. Yeah. But now what I want to kind of discuss is there'll be some problems for which, even though you will have a nice query algorithm, I will kind of show you one problem where you have a nice query algorithm, which you can come up with this Johnson graph thing, but you don't have a time efficient algorithm for it. And we kind of use that to actually show a lower bound, and I will, that was a kind of work that I did in my PhD. So I can discuss that now. Yeah? Yeah? Okay, cool. So I can erase all this, right? I'll only leave this part and I'll erase everything else. Yeah. So even this is there in Ronald DeWolf's lecture notes. So you can just check it. That's very nice lecture notes. It has all the details that I discussed today. Yeah. Okay. I'll just keep the delta value same, because that is same no matter what your graph is. Was it 1 by r? Delta 1 over r, right? Because that is just a number that depends on n and r. So, yeah, okay. Now, okay, we have something called a three-sum problem. Okay, here, again, similar flavor to this element distinctness. You are given n integers from some universe u, and your task output yes, if there exists like x1 plus x2 plus x3, or imagine you have 3 lists given. Actually, that is better. List A. Oh no, just take one. So this is a problem now. It's slightly different from element distinctness. It's called threesome problem. Now here what you have again an integers, and your task is to output yes if there exists like a triple x1 or like some xi, xj, xk that add up to the last one. Like xi plus xj should add up to xk. Now you answer no if there is none, like no tuple exists. And again, you take this promise, again, promise that if there is a yes instance, then there is exactly one triple. And then there is exactly one tuple. Okay? Like one tuple that follows this relation. So now, Beloffs showed a lower bound that if you just ask queries like, oh, give me x1 value, give me x2 value. If you just ask queries like that and you want to minimize the number of queries that you're asking, quantumly, you really need n power 3 by 4 queries to solve this. Like there is no algorithm that can do better than this. Okay, you need the n power 3 by 4 queries. Now using this Johnson graph thing, again you can kind of construct these R size subsets, and again I will plug in these values, and it turns out that when R is like n power 3 by 4, the quantum walk complexity minimizes, and you will get the query complexity matching for this. And like I said, right, like it is not only for element distinctness that you could do. Look at this. I took another problem and which has like a different complexity than element distinctness, and we are still able to give query upper bound for a different problem, but using the same kind of approach. But now what will change is the things that will change. Your delta will still remain same in the sense in terms of R, it will be still 1 by R, but your epsilon will change because now the marked elements will need to have all the 3 elements in it, right? So the number of marked elements here would then become n minus 3 choose R minus 3 instead of n minus 2 minus R minus 2. So your m will become this. So now your epsilon changes accordingly. So your epsilon is a quantity less than, so it will be, I think, R cube by n cube, I think. Yeah. Let's see if we can plug in and get all the other things. The setup remains the same, the update remains the same, because you are still going to connect 2 subsets if they exactly differ at one element. Everything else remains the same. If we plug in, let's see if it is fine. So we have R plus we have 1 by root epsilon, right? Is that...
Just one question. Why
yeah?
n minus 3?
Yeah?
Normally it should be n. Why n minus 3?
No. That time I made a mistake. So
At that time should be n minus 2.
n minus 2 also. Yes. He pointed it out. Remember? Yeah. That's why we were missing a n factor there. Yeah. So, yeah. And this is still root R, right? And update is still almost constant cost, so we'll ignore. Checking is 0. So let's try to balance this. Here we get n3 by 2 by R. So R square is almost n3 by 2. So R is n3 by 4. Yeah? You see? Like everything, yeah.
Can you again explain why we can neglect this like storage, like you added here?
Yeah, this checking cost, right? So because in this kind of procedure, when I'm making the setup stage itself, that time itself, I am asking the computer, I'm asking the graph, give me all the values of like this R size subsets. So the R size subset will be set of indices, right? Suppose it was like the 3 size subset was 1, 2, 3. I'm already asking at the setup stage, give me x1, x2, x3. So once I asked, I can copy it. I don't want to bother the oracle again. So that's why I can avoid the checking cost. Yeah? Okay? But so now the query complexity for this threesome very nicely also turns out to be this, this notation is when something is tight, meaning the algorithm, that you know matches the lower bound. Lower bound is like instinctively for the problem, and upper bound is like the existence of the algorithm. So when you have something that matches the lower bound, you know that you cannot improve further than that. Like that's the best. Yeah? But now this algorithm is not time efficient. Like even though you can make it like work in this many queries, the amount of time it requires is still linear, which is like a gap. People have not been able to improve it. And in my PhD thesis, we worked on some results kind of saying that, oh, if you cannot, because you cannot improve threesome, like the complexity of threesome, if you believe that this is the best you can do, like if you believe the time complexity is really n, then there are some other problems whose time complexity also have to be n. So we kind of gave something called reductions from threesome to other problem. So maybe we can take a tiny break and then I can discuss that part. Yeah? Okay. I might not have enough time to discuss exactly how we fit in the work framework, but I will at least point to what, how we, like where we use it, okay? Yeah. Okay. Can I resume now? Yeah? So now this is the last part of our lecture, 3-part lecture series of today. And now I will discuss what I kind of did in my PhD, okay? And I will not really tell the result that involved quantum walk, but I'll only point where exactly we use this quantum walk, okay, because we don't have time. Okay, now, in like, as a computer scientist, I would say, it's like we saw, right? There this concept of something called lower bound that I showed. Like I said, oh, you know, Beloff's proved a lower bound of n power 3 by 4 for threesome. I made such kind of statements. And then I said, now we give this algorithm, so which was also n power 3 4 queries, so we made it tight. Like I made such kind of statements, right? Now, what does these statements mean? First of all, what this statement mean is a lower bound is nothing but an argument, in some sense a formal argument, which says that no matter what algorithm whoever writes in future, ever alien writes, we don't care, because we have fixed this computational model and we have fixed this problem, this any algorithm would require this many queries. That is the essence of lower bound. So it is not dependent on what algorithm is solving that problem. It is kind of dictated by what kind of problem you're solving and on which computer you're solving. Are you solving it on a classical computer? Are you solving it on a quantum computer? It kind of depends on the model of computation and it depends on which problem. Now, the sad part is when we are having these query as a resource that we were calculating and we were doing, we have techniques to show this lower bound, okay? But when it comes to time, like if I want to show some argument that says, oh, for this problem, I really need some n power 5 by 100 time or something. If I want to say such arguments, then we do not know of techniques that can give us such arguments. So what we resort to is a different kind of technique. We resort to something called conditional time lower bounds. And the phrase will be clear soon. Conditional time lower bounds. Okay? Now the emphasis is on conditional. And this kind of research is called, like, it's done very well, like it's very common in classical complexity theory. They are called fine-grained lower bounds. Now the kind of things they study here, they have some key problems, okay? Like I will not define all the problems, but one of the key problem is threesome. So this I will touch. And I'm just giving examples of some key problems. There are many more key problems. So they kind of study some key problems and they kind of see how the complexity of these key problems relate to complexity of other problems around it, okay? Now, for example, like threesome had this problem, right? Threesome was You have like some n integers in a universe. You want to know if there exists a triple, x1, xj, xk, something like this, right? This was the question the threesome was asking. Now, there could be some other problem. There could be some completely different problem, which is like some geometry problem or something, like geometry problem. Like, are there, like, for example, something like given n points on a line, in a plane, are there 3 points on n points on a plane and some n lines? I'm just making up some problem, okay? Are there 3 points on a single line? Like, this is a valid geometry problem, right? Like, if I can give you some n points and I give you some n lines, and the task is to find out if there are like 3 points on the line. Like, that's a valid problem. Now, imagine I want to kind of understand the complexity of problem in relation to the complexity of this problem. What do I mean by that? So if I have to solve this problem, if I can take the instant of this problem, map it into some input instance of this problem, so that if an algorithm solves this, I can use that algorithm to compute an answer for this. You get what I'm saying? I'm kind of reducing my problem of threesome to some other problem. Okay? This is like a reduction I'm giving. Now, if an algorithm solves geometry problem fast, like really fast, then I can maybe solve my threesome problem very fast, right? So in some sense, this reduction will give me a new technique to come up with a different algorithm. But what if you can never solve threesome actually very fast? Suppose the situation is, oh, you cannot solve threesome fast as all. Then what you are implying is, you cannot even solve the geometry problem fast because you gave a reduction. So if there was an algorithm that solved geometry problem very fast, then I can use this algorithm to solve threesome problem also very fast, which I don't believe exists. So the algorithm for this also should not exist. So this kind of argument of arguing that, oh, there is a lower bound for geometry problem based on some lower bound for threesome is called fine-grained complexity. And that has been studied classically a lot. But quantumly, there were very few papers. So this is what I worked in my PhD. And now we have some more papers, so that's good. Now I can discuss like the reason why I even brought this up, because we kind of looked at this threesome problem, like we looked at 3 key problems, CNF SAT, threesome and APSP. But the reductions that we gave from threesome involved the walk that we discussed. So I thought it was still nice to mention. And I'll show you the challenges in a second, okay? Yeah, so the setup is kind of clear. So we are going to argue a lower bound for some other problem based on what we believe could be a lower bound for our threesome. That's kind of the setup, okay? Okay, now let's look at it. Just too jingly. Okay. Now, let's come back to the classical world again. Okay, so this threesome problem. We have x1, x2, xn integers in some universe. Output, yes, if there exists I, j, k distinct, such that xi plus xj equals to xk, okay? Yeah, now what is the complexity? What is the time complexity of this problem? Okay, classical, yeah? Now, can someone tell me a naive algorithm to solve this? What can I do? Like, we are in the classical world, no quantum, no superposition, nothing. I just want to solve this problem. I have n integers that are given to me, and I want to kind of check if there is a triple that behaves like this. Yep. Yeah, and not even in the universe, because I'm given this set. Like, yeah. So what will be the complexity of your procedure that you mentioned? Yeah, and choose 2 n square pairs. Yeah. But this checking also would take some time? Into n. For every pair, you will be checking n times, right? No, into, like times. Yes. Yeah, into is a very Indian way of saying times. I don't know. Yes. Yeah. So the algorithm that you mentioned is having this complexity of n cube-ish time, right? But let's do something smarter, okay? Now someone gave me this x1 up to xn. Let me take around n log n time and sort it first. Let me do that first, okay? So I pay n log n time, pay this much time to sort first. Yeah? Now, do the same algorithm that she suggested. I will go over all n square pairs. So I will run a loop, like loop over n square pairs. And for every pair, check if x plus y, for every pair xy, check if x plus y is in this list, sorted list A. Yeah, can we do that? Now, how much will this step take me? Because the list is already sorted, I can do a binary search, right? So instead paying n cost that was being incurred earlier, I will only pay log n cost, right? I did pay an extra additional factor here, but that was only like an additive factor. So now the total cost comes up to n log n plus n square times log n, right? And that is better than n cube, right, for large values of n. So we have a better algorithm, okay? In fact, there is also another algorithm, like little tiny bit smarter, where you can even improve on these log n, not this log n, but this log n factor. You can actually compute this threesome in n squared time by doing a little bit of pre-processing. Just give me a second. Sorry, I need to drink. Was this the pen? Yeah, okay. So there is an algorithm for n square, okay? Now, a lot of people try to improve, like further improve, right? I mean, from n square log n, they could go to n square. So the hope was, okay, maybe we can even do better. But they were not able to improve even beyond like to n square minus some epsilon, which is even very close to 0. Even that improvement is not known yet. So then what they started trying to say is maybe threesome actually requires n square time. And they started saying that as a conjecture. The threesome conjecture became that solving threesome on n input would require at least n square amount of time. Okay? So now let's call this threesome conjecture. Okay? Now if I told you, let's try to think this conjecture is what it is. If I ask you, what is the time complexity of sorted threesome? Like if I'll define a problem called sorted threesome, and I want to ask you, like if we believe that threesome conjecture is true, can we then give a lower bound for sorted threesome? And the sorted threesome is like the sorted threesome problem is saying sorted threesome says you're given x1, x2, xn all in sorted order already. Sorted order. Output the same thing. You output the same answer, but your input is given in sorted order. Like that's given. So now if I believe in threesome conjecture, can I conclude a lower bound for sorted threesome? Yeah?
So if we have n squared, but sorting it takes n log n,
Yes.
of course we can say like n log n is basically nothing, so
Yeah.
it shouldn't change.
Exactly. So like his argument is completely like correct, and what this is exactly what I want to say. Now I would say sorted threesome also requires n square time if this threesome conjecture is true, because you can always take the input of threesome classically. You have n elements, sort it, pay n log n extra time. And then if there was a faster algorithm for threesome that actually solved it in n power 2 minus some epsilon for some epsilon greater than 0, then you are ending up having this much plus n log n time algorithm for threesome, which is still less than n square, right? So you're falsifying the threesome conjecture. So what I've kind of shown as of now is if your threesome conjecture is true, then your sorted threesome also must require n square time. Yeah? This is a valid implication? Okay. Now, let's look at this entire picture quantumly. Now, what happens quantumly is slightly better, also slightly worse, but worse because it makes life easier, harder. Yeah. So now see, yeah, good. So this, I mean, you're also allowed to use randomized reductions. You're allowed, but people don't know even of randomized algorithms that can improve, like with the epsilon as a constant. There are algorithms that improve on like some polylogarithmic factors, but not in the exponent. Yeah. Okay. Now, quantumly, the threesome conjecture is falsified because quantumly I can solve threesome in actually almost n times log n time. Okay? And what I will do is exactly the same procedure like what we suggested for the threesome algorithm, the algorithm that you suggested. I am going to first sort. I will pay n log n to sort A, okay? Now, quantumly, I can't sort faster. There is a impossibility result known that I cannot solve faster than n log n. Now, I will loop over n square pairs xy and check for every pair. For every xy, I check if x plus y belongs to sorted A. Yeah, that was my algorithm, right? This quantumly also would require log n time, because binary search I can do it in log n time, that's okay. But this loop over n square pairs, I can now use my Grover. We have not discussed Grover, but Grover gives me a quadratic speed up. So just believe me on that. I can use that. So now suddenly this looping over n square pairs, even though I'm actually looping over n square pairs, but because I'm doing it in superposition and quantum, I only pay n cost for this outer loop, and for the inner loop I pay log n, and for the sorting I pay an additional n log n. So in this, like some constant factors to n log n, I can solve threesome quantumly. So clearly the classical threesome conjecture no longer holds in the quantum setting. So then people try to improve the quantum algorithm. What if we can do better than n log n or better than n? Until now, people have not been successful, even though the query bounds are better, but the time bound, the best people know, are around n log n. But now if I ask you the same question, okay, so then the quantum threesome conjecture was that threesome requires n time on a quantum computer. Okay, this is just basically a quantum version of the threesome conjecture, but this time it's not n square and it is n. Now, if I ask you the question, what about sorted threesome on a quantum computer? Can I say something now smart? Like, if I believe that the quantum threesome conjecture is true, can then I say that sorted threesome conjecture for the quantum version should also require n time? Now I cannot, because I cannot use this trick anymore. And now my sorting, like I can't do this anymore, because if I take my input, I sort it, I already am paying n log n to sort itself. Then even if some algorithm was using like less than n for the sorted part, like say it was using 1 minus epsilon, this is still the dominating term. In the earlier case, this was not the dominating term, so we could ignore the reduction cost. But in this case, the sorting, the reduction that we are doing, is dominating this, so we can't say anything using the same reduction. So now we have to do something complicated. And that is where we came up with a walk-based approach to kind of say that even for sorted threesome, you really need like n time. But the way we did it is like we kind of ran our quantum walk algorithm and Johnson graph, and like we argued using those tricks that we discussed today. And once we could argue that, sorted threesome on a quantum computer is still hard as threesome, then we were able to show lower bounds on other interesting problem. Because sorted threesome is not really that interesting. It's actually the other geometry problems and all that we discussed. Like I mentioned one geometry problem. It's for those kind of interesting problems we showed lower bounds. So yeah, this is, so the walk, like the reason I wanted to discuss this, it's like the walk-based algorithms were not just important from algorithmic point of view, not to just give you algorithms, but they were also very helpful to argue lower bounds, which I find really cool. So yeah, okay. I think I can stop now, do we? Okay, we are like half an hour earlier, that's okay? Yeah? Uh, oh, we are on time. Oh, okay. I thought, okay. Okay. Yeah, the questions, yes. Yeah. Yes. I can give you, like, I had a discussion with someone, and I can give you some references for nice lecture notes which discuss topics, like kind of topics that we discussed. Maybe then you can take a picture. Yeah? Yeah. Yeah? Yeah?
Okay, so that's the end of the session. If you have questions, of course, and like yesterday and the day before, you'll have tickets at the exit in order to eat at the course. Yes. And then there is plenty of time for you this afternoon to work on the presentation. This place here will be closed, but the two offices will be open. Okay, and you can let your laptop and whatever you want in the two offices during lunch, because we'll close everything. And if you, when you want to come back, it will be open for you to work all together. Yes.
We have some kind of extension cord, so we can use power for that.
You don't have power for your laptop?
Well, not for ours, probably.
So if someone has some power supply for his laptop, please, because I don't have any extra.
I know.